Welcome back and very warm good afternoon to one and all presented here. Very soon we are going to start the last session of this day titled Thermal Power presented by Mr. Alok Verma, Senior Manager, NTPC, and our alumni of 2000. From Motilal Nehru National Institute of Technology. Since 2006, he is working with NTPC Limited. At present, he is working as Senior Manager of Electrical Maintenance. He has more than 13 years of industrial experience in various aspects of thermal power plants. Moreover, he is also involved in various erection and construction jobs, commissioning activities, and maintenance. Parallelly, power electronics, industrial drive, high voltage engineering, renewable energy are also his area of interest. So, thank you for joining us for this session, and I request you to start the session.
Thank you, ma'am. Thanks a lot.
Thank you so much.
And good afternoon to all of you. In fact, it's a pleasure for me to share my experience, industrial experience, and whatever we have here in this FDP program. And as we have learned that this is basically focused on infrastructure engineering. So I will try to cover what are the different infrastructures available in thermal power plant. And accordingly, I will give an overview of thermal power plant. It's basically secondary energy source. It is not a primary energy source like coal or nuclear or solar or wind energy. So electricity can be produced by the energy of other primary energy sources. Like in thermal power plants, we burn the coal and we produce the electricity. So this is a secondary energy source. And any power plant, which is it is a location basically. If it is a thermal power plant, then coal energy is converted and finally electricity is produced. Then it may be nuclear plant or hydro plant. So depending upon the fuel sources, different power plant categorization has been done. So conventionally, we are having the thermal power plants where the chemical energy of coal that is taken and final result is electricity. In nuclear power plants, nuclear energy is derived. Similarly, hydropower plant where it is hydel plants. Renewable is solar and wind. So before I start about actually thermal power plant working and its various dimensions, I would like to have a small brief idea about what is the power scenario in Indian power sector. So if you will see here, this is the total overview of installed capacity, that is power capacity in India. This is data is based on 31st August, 1 month back. So if you will see here, the thermal power generation, if you'll see, it is around in the range of 231 gigawatt, and that constitutes around 62% of total power installed in our country. Similarly, next to this is our renewable energy, which is now quite dominating. Now it has gone to 88 gigawatt of capacity, ranging to approximately 24%. Next to this is hydropower sector, then our nuclear energy. So right from beginning of evolution of Indian power sector, which was predominantly by thermal power plants, coal was abundant. There were not that much stringent pollution norms, environmental norms. land were quite easily available. So at that time, this percentage, which is now 62%, was quite large, and even 80% kind of range. So this has slowly reduced its contribution, but still, Indian power sector is based on basically this thermal power generation, and which is working as a base load for this country. Is it audible to everyone, right?
Yes,
Hello,
sir. Yes, sir, it's
audible,
audible.
right?
Yes,
Okay,
sir.
thank you. Now, coming to next, if we'll see how the Indian power sector has evolved. So before 1956, it was a very introductory stage. And if you see the power capacity at that time, in 1950s, it was around 1500 megawatt kind of thing. So that was a very preliminary stage. And from 1956 to 1991, then here was the nationalization stage. And in this period, that in 1956, industrial policy revolution enacted. At that time, there were several infrastructure bottlenecks, resource constraints in power generation, huge power losses, subsidies, all these kinds of these were creating lacuna in the development of Indian power sector. Then came the era of 1991 to 2003. Here, the one of the most important act came, that is Electricity Regulatory Commission Act 1998. This act enacted to form regulatory commissions like for central electricity regulatory commission, similarly for state part, state regulatory commission. So from there, some policies and legal point of view, various hurdles were removed, and it was tried to have a growth in the Indian power sector. Then till now, after 2003 onwards, people might have heard Electricity Act 2003. This one is the biggest act which has created a path for development of Indian power sector. And with this act, our Indian national electricity policy was framed, and it advocated basically the competition among various power sector players like generators, and different state role was defined, center role was defined, and to have a competitiveness and healthy environment. So this we can see this 1948 Electricity Supply Act, for which formed the State Electricity Board. Then around 1976, there is a formation of NTPC, National Thermal Power Corporation, National Hydropower Corporation, Nuclear Power Corporation, or the national under the government of India were formed to have rapid growth of Indian power sector. Then in 1992, tariff fixation policy has came, and finally in 2003, this Electricity Act 2003. This one is the biggest landmark act in Indian power sector history. So this is how the power sector has evolved in India, and at present, India is the third largest producer as well as consumer of the electricity in the world. Our ranking is third. And if you see installed capacity wise, we are fifth. So though we are capacity wise fifth, but we are producing at third number. And power sector, this is one of the pillar we can say for the growth of country, because many of other industries are dependent upon electricity to have sustainable growth. And in the scenario of growing population, increasing rural electrification, then per capita consumption is increasing year by year. This will further put focus on power sector, and growth will be very, very high. This is a chart. If you can see here, this is showing the generation in a particular any year. We have taken this is in 1990. What was the scenario then till 2019? We are having this data, and if you see, India is third one. This one. This is producing in 2019 1614 terawatt hour of energy. So this China is first, then is US, then our, India is third. So although power generation has grown more than 100 times since independence, growth in demand has also rapidly increased due to various economic activity. And now, globally, India's major energy firms have made significant progress. Many of the companies are worldwide known. So, this is shown per capita energy consumption, energy growth. Per capita energy consumption is nothing but kind of per person averaging. So, if you will say that in financial year 16, it is around 1075. Now, in latest one is 1181. So this growth is going to increase year by year. So India's power demand is also rising very fast. Many of our industrial activities, then rural electrification, then government schemes to provide power for all these are creating huge power demand. And one of the estimate, it says that by 2035-36, there will be 690 gigawatt of demand. And roughly, if you see for India, there is a electricity to GDP elasticity ratio. This is a rough ratio which is linked with the GDP to electricity consumption. It is around 0.8. So if we see that if India has to grow by 8%, then 8 into 0.8, this much growth will be necessitated in electricity growth. So 6-7% growth in electricity year by year it will be required. So power demand in future is also going to be very, very high. Then electrical vehicle penetration. This is also in coming days will put significant power demand in the power sector. This is how the power demand has grown. We have data from 2009 to this one, 1920. Then these are the estimated one. It is growing year by year. Now, coming to our main topic of overview of thermal power plant. So, I would like to cover what are the major areas, what are the major infrastructure available in any thermal power plant. So, as we know that in any thermal power plant, when we think of as a common man, we think of coal is burnt, and we think that this electricity is produced. So one of the major component is coal handling plant. So where we have to collect coal from coal mines, and at within the thermal power plant premises, we have to handle it as per the requirement. We will. So this is one of the coal cycle. We will see later on. Then coming to boiler or steam generator. What we do from coal, we produce the steam ultimately, which runs the turbine. So this one is the boiler or steam generator, we say it. Then turbo generator is turbine plus generator combination. This is a one set. This is turbo generator set. Then if you burn the coal, there is a obvious that some ash will be produced, and it is a huge quantity in the range of 30-40%. So that much amount we have to handle. So there is a separate ash handling system in power plant. And then there is a requirement of cooling towers to cool the in a closed cycle and cool the steam. It is works in condenser cooling system. Then what is the water treatment plant? Normally we treat the plant which we get from either from any river or some reservoirs before using in the power plant. Water treatment has to be done, and this is done in our demineralized power plant, we say DM plant. And DM water is used at various process in the thermal power plant. Then finally, this is switchyard. This is an electrical system where the electricity generated by the generator, it is finally linked to switchyard for further distribution and transmission at different level. So these are the major infrastructure. We can say it is in a thermal power plant. In fact, thermal power plant, it is a large complex system, a large system. And within this also, if you see small systems also, they are having very complicated. But I have tried to cover this in a simple manner so that it will be easier to understand for everyone having different background and different streams. Am I audible now? Am I
Yes.
audible?
Yes.
So if any doubt or concern, if will be there, you can ask, no issue.
Sure, sir.
So this is layout of a typical coal handling plant. As we know that coal will have to be handled properly. So to run a power plant, approximately 3 lakhs million ton, we keep it as a reserve because we the coal is transported through Indian Railways up to some part, and within the plant premises there is railway siding, railway tracks, and everything of railway kind of thing of the power plant owner itself. So inside the plant boundary, uh, the further railways activities, wagon handling and all those is carried out by some the plant owner. So if you will see, coal is transported via railways up to a certain point. Where after that, Indian Railways stops and hand over it to the plant generator. And see, this is a wagon. Wagon is coming to here within the plant boundary, filled with the coal. This entire coal now we have to handle a wagon tippler. And what is this wagon tippler? If we will see this is a wagon tippler. If you will see this is a coal filled rack wagon. So initially, this is the platform which will be horizontal like this. Train will come, one wagon will be taken on it, and this is hydraulically entire wagon is tilted, and coal is uh, sent back to some downward, and this is now empty wagon. When we turn this is empty, and it is shifted again. So one by one rack is emptied. So this is a huge structure and hydraulically operated. So this is called wagon tippler, tippling of wagon. So this is wagon tippler is coming. Now this wagon tippler coal is coming to this hopper. There is a hopper, big steel structure kind of thing, where the coal is continuously. This is tippling is continuous. This is coming in hopper, and this is a feeder. This is a belt kind of thing. So this is transporting this coal from this wagon to ultimately here. These are the conveyor belts. Conveyor belts transport this coal to further up to the crusher house. As the coal we receive, these are having a bigger size and some holders also available in that. So this first comes to the crusher house, wherein the surge hopper is there and vibrating screens are also there. So very big boulders are screened here. So that is removed out manually, or some arrangement is there. And after this, what is the portions are coming in this crusher? It crushes the coal to have a fineness of desired mm. That fine coal is further taken here. Now, this is a far distance from main plant area where the coal is ultimately will be burned. That is boiler. So that ultimately, if you will see, this is a coal bunkers. Coal bunkers are there. From here, ultimately, it will go in the mill. This is it. This is called traveling tripper trolley. This is movement. This is also situated on the rail track here, but it is moving. So one by one, this is filled. So if you fill this one, this one, this one, like this. So this process is continuous. We get it from the railways or coal mines, and this is feeding is there in the coal bunkers for further burning in the boiler. Apart from that, there is a path also which we keep in store. That is a coal storage area. So excess coal which are not required in bunkers or for day-to-day generation of energy, we keep it as a stock. So that is done by there is a device known as stacker reclaimer. This is, if you can see, this is a huge structure. This is huge structure, and this particular one, this one is conveyor belts. This is conveyor is moving. It can move in bidirectional area. So suppose if we have excess coal, we this belt will be directing traveling like this from right side to left side. So from here to here, then if you'll see, this is a inclined belt itself. This is also a belt, and further this is also a belt. Here coal is transported, and this one is dropped here. So when we have excess coal, coal is coming like this. That coal is stored here. Same coal. Now, when there is a shortage of coal by coal mines, or we are not able to get from the railways, this is taken back. So if you this is a bucket kind of thing, this will pick it up, put on the belt, then again it will be sent back to main plant area. Then this time direction will be reverse. So this will be sent for burning at boiler. So this is called stacker reclaimer. It means that it is stacking the coal as well as reclaiming the coal also as per the desired. This one is counterweight for stability of this structure, because this is a huge structure. Now, let's understand what is the basic working of a thermal power plant. So, this is a very rude explanation. Here, if you can see, there is a coal via coal conveyors is transported. It is going to crushing equipment or pulverizing equipment. That is a mill. This is crushing to a very fineness. Very fine particles of coal are prepared here, and this one is taken to boiler, because in boiler what we need for ignition, we need coal as well as we need air also. So air is separately given to boiler. We will see later on. So here in boiler, ignition takes place. The chemical energy of coal, that is extracted, and this, if you can see, these are the tubes, water tubes. So this the water is flowing inside it. Heat is gained by this water. this is steam is getting produced, which is sent to turbine. This is turbine basically, three-stage turbine, and this is generator. So shaft, this is a common shaft on which the turbine and generator is there. So when uh, turbine rotates, this generator is also try to rotate. At the same time, electricity is produced. So that is, say, it gives a voltage kind of 20 kV. So for transmission purpose, we have lines of 400 kV or 220 kV something. In between, there is a transformer called generator transformer. This isolates the system as well as steps up the voltage so that it can be further transmitted. Now, here steam is coming, losing its energy, and low energy water and energy mixed here. So this is further cooled by cooling water. So this part is called condenser. So here condensation takes place due to this cooling water, and again this water is fed back to the boiler. So this is a closed cycle, and normally due to some evaporation and some other losses, a small amount of makeup is required. But more or less, this water circuit is works in a closed loop, and there is no separate water is required other than to cater the evaporation and miscellaneous losses. So this one part is your cooling circuit part, CW part, cooling water part. One cycle is this. One is steam cycle is this. Then we have the coal cycle is this. Then another one is when we burn this, flue gases are generated. So that flue gases we sent it to chimneys. We call it stack. These are structure of high altitude, so that all the emissions and flue gases are sent to high altitude to have the lesser impact on environment. Now, when the coal is burnt, there will be waste also, that is ash. For handling of this, there is separate ash handling system. Now, to have a feel, if you can see, this is a turbine generator set. Basically, this is a large area. In fact, if you can visualize it, this yellow part is turbine. So turbine is also having three parts, then high pressure, intermediate, and low pressure turbine. So this entire structure is, you are looking, these are the turbine. Then this part is your generator, this red one. And at the end, if you can see, this is the excitation system part, AVR we call, automatic voltage regulator. So to give the DC power to rotor of the generator. So this is called, all these things are TG set. These are valves, stop valves, control valves, all these things are here. Now, to have a feel that how the temperature and the parameters are changing, we can see from here. Earlier slide was a very crude one. Now, some modified one is this one. So what we see in thermal plants, there is a boiler drum. This one is boiler drum. This is consisting of steam as well as water mixture, and steam is separated. So this upside is stream, it is having some wetness, and we cannot directly feed it to turbine. So that wet steam is further heated in the boiler. This is a boiler part. These are tubes, superheated tubes. Steam is going, getting some additional heat, and then now if you can see, this is the main steam. The temperature of this is around 540 degrees Celsius for a 200 megawatt unit, and it differs for 660 megawatt unit if it's there around 600 degrees Celsius. So high temperature. Pressure is also 150 kg for this 210 megawatt. Uh, for higher size of units, this pressure will go high, 170, 180 like this. So high steam, high temperature, high pressure steam. Now it is going to HP turbine. This is turbine, high pressure turbine, and this is stop valve and control valve. So we have to regulate generation also. So how we do? How much you will put the steam, that much generation will be there. If you have to reduce or regulate the load, this control valve is there, and this one is stop valve. In case of any emergency, we can isolate it. So this main steam giving energy to this HP turbine, and from here the now the energy in this steam, in exhaust system, it is less. So it is again sent back to boiler to reheat it. Again, it is going to boiler. Some reheat steam is produced. So this reheated steam, again, though the pressure is low, temperature we again by do same 540 degree by heating. So HP turbine exhaust is coming here, getting reheated, and going to, now it is going to intermediate pressure turbine. So here again the output of this, it is going to LP turbine. So here in LP turbine there is condenser, integral part of it. This condenser, then again as I explained, there will be the cooling water. So this will not mix. This is a separate cycle, closed cycle. This further less energy stream is get condensed, then it is called condensate. So how it is happening? The main stream we are forming, then going to HP turbine, then output of this is reheated again, then going to IP turbine, then LP turbine, and from LP turbine we get the condensate. So now say this is a condensate or water, it is say 45 degrees Celsius. So we have pump, condensate extraction pump here. So this what we do, we heat it up, because ultimately we want this to be happen in a closed circuit. So again heating of this water is done. So that is done by some of the steam is available here, bleed steam. That steam is taken to heat in LP heaters, heat the water. Otherwise these all things are done to gain the maximum energy in the steam. Otherwise it will be waste. So after LP heater, now if you can see, temperature has gone to 120 degrees Celsius. Earlier it was 45 degrees Celsius. So here this is a vessel called a deaerator. Here 120 degrees Celsius. Then we have boiler field pump. So if you see this pump, this is taking suction from here. Then again the discharge of this is again heated, further heated. So this is now reaching the temperature of 244 degree around. So if we see, 45 degree condensate has gradually heated up, and by various steam which otherwise would have been lost, we have absorbed energy from there also. And here now this boiler feed pump raises the pressure also. This is 180 kg per centimeter square of pressure. This is feed regulating station. So if you want to regulate how much feeding is to be done, we can regulate it. Then this 244 degree Celsius water is going to economizer in boiler. Then finally it is going to your boiler drum. From boiler drum, this is coming via large pipes. This is downcomer. Then again, it is heated in where this is place where firing is taking place. So getting heat and going to in boiler drum where is the water and steam mixture, and this cycle goes on in this manner. So this is a closed path. Closed path. When this turbine, due to this steam rotates integrally, there is a generator also, and electricity is produced here. So that is further transmitted. Here in boiler, we have to put air also, and this is a cool path. So this is an overview. Now, if you will try to
Excuse
understand,
me, may I ask, sir, may I
yeah,
ask a question if you allow?
yeah, sorry, yeah,
Sir,
tell me.
in the previous slide, you were saying that the capacity of a generator is M 247 MVA.
Yeah, right.
Sir, how do we estimate? Basically, we are providing energy in the form of units, like kilowatt hour. So, how to transform that much energy? If I wish to identify कोई पावर
No,
स्टेशन है वो इतनी इलेक्ट्रिसिटी प्रोवाइड कर रहा है एंड हाउ टू एस्टिमेट दैट वैल्यू
see, whenever power plant is designed, no, at that time, the rating of generator and turbine is fixed. For example, say this is a 210 megawatt turbine. Okay, its rated capacity is 210 megawatt. तो सपोज इसकी 210 मेगावाट इसका रेटेड कैपेसिटी है ना? तो अकॉर्डिंगली जनरेटर की कैपेसिटी भी फिक्स्ड है, ठीक है? सपोज इट मे गो अप टू 230 megawatt like this. Okay, so beyond that we cannot run the system. There are various protections available. वो हमको आगे जाने से रोक देगा, ठीक है ना?
So
तो
if I wish to know कि generating any quantity of electricity in kilo, how to estimate that value?
your voice is not audible.
सर अगर अगर
थोड़ा
अगर मैं ये
क्लियर बताइए.
जानना अगर मैं ये जानना चाहूँ कि कोई थर्मल पावर प्लांट है वो कितना
हाँ
इलेक्ट्रिसिटी जनरेट कर रहा है
हाँ
तो
हाँ
वो मैं कैसे पता कर सकता हूँ लाइक जैसे आपने इसमें कहा कि 210 मेगावाट इसकी कैपेसिटी है तो क्या मैं ये 24 घंटे चलता थर्मल पावर प्लांट
अच्छा, okay, I got your basic question. Okay, for that
जी
you
जी
have to simply what you have to do, that whatever megawatt you are generating, that you multiply by time. Okay, suppose
जी
this unit is run 1 hour for
किलोवाट आवर
suppose you can convert megawatt hour into kilowatt hour by multiplying 1000. Okay, सो अगर 200 मेगावाट चलता है ये 1 घंटे के लिए, तो 200 मेगावाट आवर हो गया, है ना? सो
जी
अगेन फिर सपोज 100 मेगावाट चलता है क्योंकि डिमांड कम है ना? तो 100 का 100 मेगावाट आवर हो गया, ठीक है ना? ऐसे आप कम्युलेटिव कलेक्ट करते जाते हैं, है ना?
सर कोई स्टैंडर्ड टाइम फिक्स नहीं होता कि 24 आवर्स चलता है या 8 आवर्स चलता है ऐसा कुछ फिक्स नहीं होता है
No, it is in fact very dynamic condition. Okay, so for your information, अभी तक का जो है मिनिमम 15 मिनट्स का ब्लॉक रहता है, ठीक है?
16 मिनट्स का
15 मिनट का एक ब्लॉक, जो हमारे पास जितने भी पावर सिस्टम ऑपरेशन के जितने डिस्पैच सेंटर्स हैं, जो लोड डिस्पैच सेंटर्स हैं, एंड जो पावर सिस्टम ऑपरेशन के लिए जो पूरे कंट्री में 5 जोन्स हैं, वो पूरा देते हैं, ठीक है? एंड इट इज ए डायनेमिक कंडीशन. तो वो नेक्स्ट ब्लॉक के लिए हर ब्लॉक 15 मिनट इज कॉल्ड वन ब्लॉक. सो उनके पास से डाटा ऑनलाइन आता है कि ये जैसे अभी सपोज 130 होगा, तो 130 to 145 यू हैव टू जनरेट सपोज 100 मेगावाट. ओके, तो at that time we have to generate it 100 megawatt, ठीक है? अभी नेक्स्ट ब्लॉक के लिए उन्होंने बोल दिया कि वापस हमको 150 चाहिए, तो वी जनरेटेड 150 मेगावाट आवर. ओके, एंड और जो
It is
आपका
a controlled process. It is a controlled process.
और
This I get
जो
the.
हाँ, for वन मोर थिंग आई वुड लाइक टू ऐड, जो आप कैलकुलेट करने ना, वो मैनुअली कैलकुलेट करने की जरूरत नहीं पड़ती. वी हैव एनर्जी मीटर्स इंस्टॉल्ड. ओके, तो दैट एनर्जी मीटर, उसका रिस्पांस टाइम सेकेंड्स में रहता है. तो कंटिन्यूअसली व्हाट इज द एनर्जी इज फ्लोइंग एंड टाइम इट इज मल्टीप्लाइंग. ओके, so that is giving the energy on continuous basis.
Thank you, sir.
Okay, thank you. So what we have seen here, that there are different cycles. There is a coal cycle, there is a cooling water cycle, there is a steam cycle, then this one is a green color one is water cycle. These all are working in a closed cycle kind of thing, and they have their own functioning and on process. So this is a overview kind of thing where we can understand how it is being controlled also. Now this one is your coal part, then ash handling part. Then if you see a boiler, if you are going let it go the flue gases out, a large amount of temperature and energy will be missed. So before sending it to chimney is here. First, it is given through different devices and different path, so that we can collect energy from flue gases also. Like superheater, some energy will be regained here. In economizer, which we have seen there, no? Economizer, this heating is being done by this flue gas. Otherwise, it was going to waste. Then air preheater like this. So before discharging it to chimney, this flue gas energy is extracted so that the maximum efficiency we can achieve. And this is alternator. Then this part is switchyard part. Now this is how any plant operator which sits on the control room, they are having a screen like this. This is one of the screen I have just put here to have a feel that how it is operating. So if you can see, this is a CMC. This is CMC means coordinated master control. That these are the fully automatic systems. Every process is automated and they work in coordinated master mode. Everything is coordinated. So these are the current. Suppose this is the speed of the turbine 2932 RPM at that particular time. How much megawatt is generated? What is the current frequency? Because according to frequency also we need to regulate. So how they are working? This is the milling systems. Milling systems. Coal is coming in the mill, and how this is transported. So after the particular, we need air also. So from crushing, there is primary air fan. This is taking from mill and sending it to furnace. So fine particle of coal are going to furnace. So this is primary air fan functioning. This is coal. Here it is crushed. Then air is supplied. FD fan. This is forced draft fan. This is giving air because we need air as well as coal for ignition here. And at some time when we are starting the unit, we need the support of oil also. This is light diesel oil. So when there is no coal, we take the support of oil. So this oil can also uh, support the ignition function, but it is costly. So as soon as we get synchronized to grid, this oil support is withdrawn. So this blue line is your water circuit. In actual, if you can see in a 200 megawatt unit, then LP heaters, there are 3 LP heaters, then deaerator, then boiler feed pump. Pressure at current pressure is 179 kg, if you can see here. Then HP heater, high pressure heater. Temperature is increasing gradually. Then going to economizer, then this drum, then same thing is steam is separated, so getting superheated, then going to turbine, and that, as I explained earlier, this process is going on. Now this furnace, this boiler, this is basically negatively pressurized. It means that from outside it can leak into inside, but from inside nothing, no flame, nothing can come outside due to safety reason and all. This is condenser and CW system. I explained earlier. This you can see. This structure is your boiler. This is height of this is around 90 meters, 95 meters. So any common person think that boiler will be some kind of vessel where some steam will be produced. But when in actual, this is a huge infrastructure. This is 90-meter height. Lot of things are available in this. This one is your TG building, turbine generator building. I shown you earlier. TG floor where turbine and generator set will be here. Then in between, this is the chimney. Final flue gases will be emitted here. So this is a typically how actual systems are there. Now, after the looking after the overview of thermal power plant functioning, now we see what will happen to S, because unit is running on continuous basis. So coal is burnt, so there will be, of course, S will be produced. So Indian coal is having high S content. It is around 30 to 40%. So suppose a typical 2000 megawatt unit is, station is there. So S will be generated around 9,000 to 12,000 ton per day. Huge quantity. So this quantity we have to dispose it off. And due to environment norms also, we just cannot think of throwing it away. It has to be properly disposed and properly precaution to be taken care so that no pollution will occur in the surrounding area.
Good afternoon, sir.
Yeah, please.
Sir, I have a question that is there any technique to reduce air pollution in power plant?
Yeah, there are techniques, and I will cover in next slides. Okay, in coming slides.
Okay.
Okay, actually, two kind of S is generated. Okay, one is bottom S called, and another one is called fly S. So there is a infrastructure called electrostatic precipitator. Okay, so that collects these flying S's. Okay, and that reduces the amount of S going in that stack. I will cover in coming slides. Okay.
Okay, sir. Okay. Thank you, sir.
So if you will see, 20% of the S below the furnace is known as bottom S. These are relatively thicker, and 80% of S is carried away by flue gases. So that is known as fly S. So bottom S, it can form slag and clinker depending upon the temperature. Suppose if temperature is X, at that time some clinker formation will be there. Temperature inside the combustion zone is Y. At that time, condition will be different. So this one, what I told, fly ash is collected through electrostatic precipitator, and fly ash disposal system is there. So that is a separate. we will see in the next class. So if you can see, this is coal yard. From coal yard, we are ultimately pulverizing it to pulverizer. This is a fine mess. Then in boiler, it is going. Boiler having your bottom ash at fly ash. This bottom ash collected in bottom ash tank. Then fly ash is passing now. Now next. So if this is a electrostatic precipitator, if there is no electrostatic precipitator, this flue gas will carry fly ash almost maximum. So to avoid that and to reduce the pollution, this is in between ESP is installed, and depending upon this one of the, this is called pass. Just as, for example, this is 4 pass. If we want to further strengthen, then we will increase the pass in design. So there may be some ESP having 6 passes. So that will collect the ashes more efficiently. So this slide, if you can see, this pulverized coal is burnt here in the furnace. Temperature is very, very high, 1300 to 1500 degrees Celsius. So here we directly get the bottom ash, around 20% of total ash. Then some ash is collected in economizer, that is eco hopper is there. There we collect some 1%. Then air preheater, there is also 1% chance. Then this is a electrostatic precipitator exclusively installed to collect this fly ash. Otherwise, it will go to stack and pollute. So this fly ash is around 80 to 90%. Now you can visualize it. Then these are the hoppers. In hoppers, we collect it, that ash, and these are ash pipelines. It is through air, it is sucked and sent to some another storage tanks for further discharge of all the ash. This is ESP. This is ESP. This side, left side is boiler, and this side will be your chimney. Flue gases are diverted to this. So this you can say, this one is one pass, then this one is another pass. So flue gases are passed through this electrostatic precipitator. So when they pass through this, fly ash is collected, and there is a wrapping mechanism. I will show how it is working. These are the wrapping motors. So this is the electrostatic precipitator installed in between. This is boiler. This is ESP. This is stack. Now, how it is doing? In ESP, we are having the plates. These are the plates. Yes, these are charged plates. Externally, these are charged through DC voltage. So when this flue gas is coming from this side, entering this side, flue gas is getting out. So in between, since these plates are charged, there is solid particulate matters are in flue gases. Okay, so this will be charged and attracted on these plates. These plates, so there will be a collection of SS here in all these plates, and these plates are hammered on certain interval. So all S falls down in a hopper. So from there, separately it is collected. So this is the principle of electrostatic precipitator for collecting the ash particles. This is how these are the chimneys. These are very long structures, so that even though small amount of that polluting elements are there. These are discharged at high altitude, so that impact in the normal surface level, it is very, very less. These are conveyors. Coal is transported like this. You can see this is boiler, this is turbine building, this one is cooling tower. We will see. So this is typically aerial view. Now coming to cooling water system. So this is a huge infrastructure. This cooling tower you might have seen. This is a long tall structure. The function of this is there is turbine after LP turbine condenser is there. So for condensation process, this water is required, cooled water. So that is flowing in closed path this way, and then going to condenser. Then steam is condensed here. Then again, hot temperature water it is there after here, gaining the temperature in condenser here. This hot temperature water is going to cooling tower, and it is cooled here. How the construction, we will see the next slide. This one. This is called natural draft cooling tower. Its height is also very, very high. So bottom of this is cold water basin. This is cold water, and hot water which is coming from condenser. So that is at a certain height. This pipe is connected, and there are nozzles like spray arrangement. So this hot water is sprayed, and from structure is such that civil design is such that there is a air flow from bottom to top. So hot water is sprayed, then air inlet is from this side, and air is taking the energy from this hot water, getting water is getting cooled and coming to cold water basin, and then warm air is going upside. So this is the principle of natural draft cooling tower, and this you can say it is photo from one of the site is construction phase, how it is constructed. It is a tall building, so a risky one also. So we have to be very, very careful. Now another kind of cooling tower is forced draft cooling tower. So this one is natural draft, very tall. This one structure wise height is less. So what is the difference? Difference is we have forced cooling here. We have installed the fan. This fan is cooling the hot water which is coming here. Hot water is getting entered here, and this is rotating and cooling the water. Every other arrangements are same. So this is regular power consumption, and that earlier one is one-time job. So one-time expenditure, and this one is regular expenditure, but structure is small. This is how real looks like. These are fans, fan. So this is cooling the water coming from hot condenser. This is, if you can visualize it better manner, hot water is coming in this also, in forced draft cooling tower also. Every arrangement is same. Only thing is it is naturally, and it is forced air circulation is there by means of fan unit. Now after the electricity is generated, we have to further transmit it, because such huge power we cannot handle in a standalone manner. So after generator, say voltage is around 20 kV, it is stepped up further by generator transformer. So 20 kV is further converted to say 400 kV. So that 400 kV system is connected in this entire arrangement of electrical system that is called switchyard. So before this, let's have a look of this. Suppose this is unit side. These conductors are suppose 400 kV conductors here. So these are going into the switchyard from main plant side, and this one these conductors, this form a bus. This is called bus. So one line is there. Suppose Vilai line is this. Suppose another line is this. All are taking in out is taking from these conductors. So these are the bus point. So typically, architecture wise, if you will see, there will be the incoming, there will be outgoing, and there is two such kind of bus is there. Main bus one, main bus two. So that if in case of any issue in any one bus, at least power generation should not hamper. So this is main bus one, main bus two. This is bus coupler. We can even couple this to buses to have same potential level. Then there are a switch. There is isolator like this. There are breakers, CTPT. All these arrangements are there in switchyard system. And finally, from switchyard through these tower lines, the power is evacuated and sent to. It is connected to other places through transmission lines. So this is how from coal to electricity is produced, and final uh, entire functioning is done. So this is all about thermal power plant. This was a small presentation. We could not, because in this 1 hour duration, it is not possible to touch uh, various aspects.
Excuse me, sir.
Yeah,
Sir,
please.
can you please again little bit tell us transmission of the electricity because the because at the power thermal power station is a huge amount of electricity is generated na? So
Yeah.
there's a hierarchy na, by which it is getting reduced and approaching to the domestic houses. So can you please elaborate that stepping down process of electricity into various substations if possible?
Sorry, can you repeat your question, please?
So can you please tell us the hierarchy of stepping down of the power of electricity at substation by which
Okay.
it approaches to the domestic houses, sir?
Okay.
That stepping down hierarchy of the power, sir.
Okay. Let me tell. So, if you see in power plants, generated voltage is 20 kV. Okay. So, we have to transmit it to the long distance. Okay. So, that is further stepped up to 400 kV system. Now, since this is a concept of grid system, all the systems in the entire lines, generators, and every other substations of countries interconnected. Okay, so we when we are putting this entire energy at switchyard, from there it is connected to another substation or another lines also. Okay, so from there 400 kV transmission line will be there, for example. So that will go to some other substation of transmission companies. Okay, so from there they will, depending upon the power handling capacity, further there is state governments on substation. Suppose it is a 66 kV substation is there. So depending upon their infrastructure, that further it is stepped down, and ultimately for household we need 415 volts. So that is done at distribution level, and whatever the generators, that is power plant operators, we measure the power at bus only, that is switchyard only. Okay, rest of the entire part is taken care by the power grid. Okay, so accounting for everything,
Sir,
that how much.
when we are
हाँ,
referring URDPFA guidelines ना, तो they are
हाँ,
saying कि शायद 15,000 कैपेसिटी के लिए एक 11 किलोवाट का सब स्टेशन होना चाहिए, तो उसका
कैसा कैसा
मतलब वो गिविंग द थंब रूल ना, मतलब फॉर 15,000 पॉपुलेशन देयर शुड बी वन 11 किलोवाट का सब स्टेशन।
हाँ, ओके ओके,
तो
सो
सर वो हायरार्की कैसे हम काउंट करते हैं, लाइक 66 कितने
बेसिकली
चाहिए
देयर
होते
इज,
हैं?
हाँ, इकोनॉमिक्स इज इन्वॉल्व इन दैट। उसमें क्या है कि जैसे सपोज पावर रिक्वायरमेंट कम है ना, तो वहां पे मैं कोई बहुत बड़ा सब स्टेशन नहीं बना सकता हूँ, ठीक है ना, और पावर रिक्वायरमेंट मेरी थोड़ी ज्यादा है, तो मुझे उस हिसाब से पावर हैंडलिंग कैपेसिटी भी थोड़ी मुझे ज्यादा रखनी पड़ेगी। एंड ये पूरा जो इंटायर गाइडलाइंस बनती है, उसमें कई सारी चीजें हैं। सिस्टम की स्टेबिलिटी का ध्यान रखा जाता है ना, सिस्टम की स्टेबिलिटी का है, देन ओवरलोड कैपेसिटी का है, कहाँ पे लोड डिस्टरबेंस होने से क्या है, कितना वोल्टेज पे कितना डिप पड़ेगा, ये सारी चीज़ों को ध्यान में रखते हुए ये पूरी सारी चीज़ें लोड फ्लो स्टडी की जाती है, और उसके हिसाब से ये सारा चीज़ें फाइनलाइज होता है।
तो एक चीज बस और पूछ लूं, बस ओनली वन लास्ट क्वेश्चन।
हाँ,
11 किलोवाट का सब स्टेशन मतलब इस पर तो रिलेशनशिप है किलो?
नहीं, दिस इज एक्चुअली दिस डिपेंड्स अपॉन, जैसे आप स्टेट से स्टेट वाइज जाएंगे ना, तो अदर स्टेट का अपना अलग अलग गाइडलाइन, ठीक है ना, वो, हाँ, उन्होंने सपोज आप छत्तीसगढ़ में आपने ये ले लिया, बाकी जगह में कुछ 11 किलोवाट इज ए वेरी स्मॉल पावर, है ना, कोई ज्यादा पावर नहीं
आई
है।
थॉट कि परहैप्स देयर इज सम रिलेशनशिप कि 66 किलोवाट का सब स्टेशन इतने नंबर ऑफ 11 किलोवाट के सब स्टेशन को कैटर करेगा, ऐसा कुछ रिलेशनशिप होता
नहीं
होता
नहीं
है?
नहीं, ऐसा नहीं है। हाँ, लेकिन क्या है, नॉर्मली जहाँ पे इंडस्ट्रियल यूजर है ना,
जी
जो
जी
इंडस्ट्री को यूज करेंगे, वो 11 केवी एंड अब ही उनको ले जाता है, और उनको प्रॉपरली सब स्टेशन के थ्रू ही देना पड़ता है ना, दैट इज टेकन केयर बाय द डिस्ट्रीब्यूशन कंपनीज इटसेल्फ। ये वही लोगों का काम है, हम लोगों का उसमें ज्यादा कोई दखल अंदाजी रहता नहीं है। यहाँ पे
जी
क्या है कि आपने जितना जनरेट किया है ना, और वो पूरी उसकी अकाउंटिंग रहती है, ठीक है ना, और
थैंक यू सर।
ओवरऑल जो रहता है वो ग्रिड का डिसिप्लिन है, जैसे कि यहाँ पे कितना वोल्टेज पहुंच रहा है, ठीक है ना, फॉर एग्जांपल कि कोई ऐसा सिस्टम बना दें कि जहाँ पे वोल्टेज को डिस्टरबेंस हो, ग्रिड की स्टेबिलिटी को प्रॉब्लम आए, तो उस सब चीज़ों को ध्यान में रखते हुए वो पूरे गाइडलाइन बनाते हैं, है ना।